This is where your must-know functions, that test we took about the parent graphs, this is where you start to have to remember them, okay, and really remember them. Because what we're going to do is we're going to take those parent graphs, and we'll probably talk a lot about the quadratic today, just that basic parabola, because it's kind of the easiest to see all the transformations on. Joseph, did y'all do transformations yet? Did you? Okay. So we'll look at that, but it's certainly not the only function that you can transform. I'll try to do some various ones so you can see. It's just good because it goes across both axes, and then you can see what happens as we move it and shift it. All right, so what we're going to do, we're going to think about a basic function like that quadratic. And this has no transformations done to it. That's why we call it a parent function. All those ones you took a test on last week, those are parent functions. Okay, so this is 0, 0, 1, 1, and I'm just showing you the points because you'll have to do some things with some of the points as we transform. Don't be so excited, Chandler. Contain your excitement. That's terrible symmetry there on that. Yeah, it's curved. -2, 4. Okay? All right, everybody agrees that's the parent function here, right? So what we can do, and on your sheet, I've got some general rules here that you can apply to find out what happens to the function as we transform it. So we start with f of x, okay? Anything that we add or subtract to the end of the equation. So on your sheet, it says f of x plus c. That means we take the whole equation and we add something to it, okay? Maybe I add 2. What that does, that c shifts my graph up or down, okay? If it's plus c, then it shifts it up. If it's minus c, of course, it shifts it down, okay? So it's a translation either up or down. So if I took the same parent graph and I said, okay, how about what if g of x equals x squared plus 1? Okay, that means everything moves up 1. Every y, and if you look at the column that says change, it says xy becomes x y plus c, which means you add that c to every y value, right? So 0, 0 becomes 0, 1. What do you think 1, 1 becomes? 1, 2. Negative 1, 2. 2, 4 becomes, what does it become? 2, 5. Okay, all it's doing is taking this exact same parabola and sliding it up 1 unit. Okay, so anytime you just throw a number on the end of an equation, that's a vertical shift. Does that make sense to you? Okay. What if I said h of x equals x squared minus 2? What is that doing? It's going down 2. Always from the parent, okay? So x squared minus 2, it would, every single point slides down 2. Again, I could take every y coordinate and I could subtract 2 from it, and it would just shoop, slide everything down. Does that make sense? All right, those are the first 2 rows, yeah. Who said Miss McGee? Okay. Must be. All right, everybody okay on vertical translations? Up, down. Those are the first 2 rows on your little cheat sheet. All right, next one I'm going to do is horizontal translations. All right, so that was vertical translations. I probably should have labeled that. I'm sorry. I titled it. Horizontal translations. So, and this is where you have to kind of think about it. Your cheat sheet will come in very handy. If I have f of x, and this time I'm adding or subtracting to x only. Okay? So it's not just tacked on at the end, it's to every x in the equation. Okay? This is a horizontal shift. Okay? And even though this is adding, it's actually a shift to the, what do you think? Look at your sheet. Yeah. To the left. Or the right. Okay? So if I have that same parent graph, that same f of x equals x squared, let me just put it on here so you see. 1, 1, negative 1, 1. What this is doing, if I said, what about g of x if it is x plus 1 squared? Do you see the difference in how I wrote that? Why that's a horizontal translation instead of a vertical? It's only to the x. This is not the same as this. Okay? This is a vertical. This is a horizontal. Yeah. All right, so you're exactly right. And if you look at your cheat sheet, it's the opposite of what you think, right? The horizontal translations, and I tell you what to do. I tell you how to make it do what it needs to do without actually plugging into the formula every time, okay? So this is a shift which way? Left, exactly. Everything's going to shift left by 1. And if you plug the points in there, you would see that that's what happens. It moves the opposite way you think on the x. If it says minus, it's going right. If it says plus, it's going left. When it's only to the x. If you plug it in, you would see. Yeah. Correct. Correct. It is. It is a little different. It'd be right. So this is 0, 0, right? So if you look at your little cheat sheet, it says if you're adding, if it's x plus c, so I'm on the third row. It says that f of x plus c, it says to do it, you take xy, and it becomes x minus c y. And that's your new one. So here, because my c is 1, right? So it's 0 minus 1, which is negative 1, 0. So you can do it either looking at the graph and sliding, or if I just give you the points, you can do that by adjusting the points on each one. When we get to the shrinks and stretches, you'll have to do it by the points. That's why I'm showing you with the points here too.
So you're going to give us the points?
No, you'll have, that's why we tested on those must-know functions, because you'll have to know those points on the parent graphs. Because we're going from the parent graph.
Yes.
From the parent graph, yep. Well, you'll put them on there. For this one, it's x squared.
So, okay, so we get points off that.
Right, or what you know, right, the same way you did on your test. This sheet? Oh, no. All right, for example, this, I think this will make more sense when we bring it all together too. Look at this. If you just saw that equation, tell me what's the parent graph here? The square root of x, right? That's my parent. My parent is before any transformations have been done. Tell me, how is this graph in yellow going to be different than the parent graph in white? What's being done? it's got close. Remember, the x is opposite. It's going to go left 2 and down 3. Okay? So my parent graph, remember, looked like this. The square root of x, 0, 0, 1, 1. Then we'll go out to a perfect square. Let's say 4, 2. Remember how I told you those graphs were so important? This is why. Okay. So now, exactly, now this one shifts and it becomes, and I'm going to do it in yellow since I wrote the equation. Every point is going left 2 and down 3. Left 2, down 3. Left 2, down 3. Left 2, down 3. So look at that yellow equation. We know that the parent is the square root of x. So from that, we're going left 2 and down 3. So every single point goes left 2, down 3. Every single one. That's all it's doing is it's taking that whole graph and is sliding it down and left. If you could just pick it up and slide it, that's all it's doing. Translations are the easiest of the transformations because all they do is slide. Everybody okay on that? One more? Yeah. Example with some translations, and then by the time we're done, we'll put all the transformations together. Let's say I had first of all, what's the parent graph? X to the third. It's the cubic, right? That's that one. No. The compressions and stuff are shrinks and stretches. Parent graphs don't have any compressions on them. Every single time, exactly. Correct. That's why I wanted y'all to test on it, because I wanted you to memorize it. I wanted to be familiar with you that you can, anytime I say what's the parent graph for a cubic, you can graph it. And you know at least points that help you get to that parent graph. All right. What is being done from the green parent to the yellow transformed? I hear to the left. Does anybody agree, disagree? What did you say, Jackson? I think it's going up too. Why do you think it's going up and not left? The +1 is tacked onto the end of the equation, okay? This, if I wanted to move this left one, I would have to write it this way. That's left 1. This is up 1. See the difference? All right, so every point on here goes up 1. There's the transformed graph. Everybody okay on that? It's opposite on there. So if you look at the equation, if it's plus C, then it's left. If it's minus C, it's right. On the end, if it's added, it's up. If it's subtracted, it's down. Whatever this number on the end is tells you how many you go up or down. So on the one before, that number on the end was -3, which means I go down 3. Well, left 2. It's opposite on that one. Those are left and right translations are opposite of what they say. Huh? What about it? No, that just tells you the parent function to use. So this f of x plus c, that's a shift left c units, and x minus c is a shift right c units. Okay, these are all on your sheet right here. That's rows 3 and 4. Y'all okay so far? Because we're fixing to get into some others. All right, let's talk about reflections. All right, so 2 types of reflection. Do you remember what reflection means? If there was a mirror there, you can reflect over y or you can reflect over x, okay? So 2 different reflections. If every single x you see is negative, okay, if you change the sign of every x, that means it is a reflection over y. And if you don't remember how to reflect, I've got a note on here that says xy becomes opposite x, y. So every x changes sign, every y stays the same. That will reflect it over y. Okay? Now, if the whole function is negative in front, okay? So if I negate everything, that's a reflection over x. So my x would stay the same, but my y is going to change signs. All right, let's do an example. All right, let's say I had, let's go back to my quadratic. These are 2 different reflections. Okay, do you see the difference in the 2? Okay. This is the first one's really the one I'm going to focus on, and you'll see why in just a second. But here, what type of reflection is that? It is going down, Cameron, that's correct. But it's reflected over which axis? It's going down, so it's reflected over the x-axis. Why is this one over the x-axis and not the y-axis? This one, the negative sits in front of the whole equation. That one, the negative sits only with the x. Do you see the difference? These get tricky when you get to things where that's the only thing there. Okay? Okay, so this one, these aren't the same equation, right? This one is negative f of x. It's putting a negative in front of the equation. This one is putting a negative just to x, if my parent function is x squared. When it comes in the front of the whole equation like that, right? So reflection over x. So how do you reflect over x? What are you negating? You're negating y. So 0, 0 stays the same. 1, 1 becomes 1, negative 1. negative 1, 1 becomes negative 1. Hampton, quit hiding behind that binder. And it flips it completely over. I will. I'll show you. This is not a great example of a reflection over y because it's an even function. And even functions are already symmetrical about y. So, and it, I will. Let me show you a different one that's reflected over y so you'll really be able to see it. Y'all okay on that? It's over. Okay, what if I do? Okay. In this case, because it's odd, it's going to be the same thing. But that's okay, because I want to show you. Let me show you. What's the parent graph? It would be the same. It's going to be the same. That's why I said hold off on that one. Let me get to this one. What's the parent graph here? The cubic, right? Okay. If I reflect that over y, what am I negating? X. This means change x because it's reflected over y, right? So it's not 1, 1. It's not 0. Well, it is 0, 0. It's not negative 1, negative 1. It's reflected over y now. All right, shrinks and stretches. This is the part I dread getting here. Compression is the same thing as shrink. Stretch is pretty common terminology. Okay, so stretch versus shrink. Now, we talked about quadratics shrinking and stretching, right? Because it makes them wider or skinnier. Cameron, that's not going to help you understand. Okay? Those are shrinks and stretches. What makes it wider or skinnier, okay? Because what happens is when we talk about a stretch, we can talk about a horizontal stretch. And let me just show you before we actually do it. If this is the parent graph, okay, a horizontal stretch, if you were to take the x-axis and you were just to stretch it out, okay, it's going to make that graph really wide, right? This is a horizontal stretch. Yes? Does that make sense? Why it's called that? Okay. What happens if I shrink it horizontally? It gets skinnier, right? So this would be a horizontal compression or shrink. Yeah, because you need to be able to recognize what's what. Okay. Now, I want you to think about something. Looking back at that white graph in the middle, I can have horizontal shrinks and stretches, but I can also have vertical shrinks and stretches. If I took that y-axis and I stretched it out, is the graph going to get wider or skinnier? Skinnier. So a vertical stretch is the same thing. Vertical stretch. Do you see why? Think about if those axes were rubber bands and you could just stretch it out, it would make that graph get skinnier, right? So a horizontal shrink and a vertical stretch are the same thing, all right? Now look at the other. What would a horizontal stretch be vertically? They're opposites, right? So this is the same thing as a vertical shrink or a vertical compression. Everybody okay on that? What time's the bell ringing here? 50? Well, pooh. We're going to have to continue this tomorrow.